In our last video, we reviewed or learned for the first time how to balance chemical equations. We did some practice with that. We also started our study of reaction types and predicting products. We are going to continue that now. The next type of reaction is a double replacement reaction, a DR for the abbreviation. Okay. And basically, it's going to be defined as a switching of partners. So it's going to consist of 4 ionic compounds, and they are all going to switch partners. These are often also referred to as exchange reactions because everyone is exchanging. So if you look at the examples, Na started with OH, but on the product side it's with Cl. And Fe started with Cl, but on the product side, it's now with OH. We can also predict our products for these. Okay, once again, you are going to make the assumption that you are producing ionic compounds, because that's what you will be producing. And you're going to switch partners. What I like to do is I just like to switch the metal with the metal. Oops, sorry about that. Okay, because it's just easiest that way, and then I know I'm always doing it right and the way that I'm supposed to. Okay, so in our first example, which we'll do together, calcium and sodium are switching. So we're going to say, okay, calcium is now with the OHs, and Na is now with the Cl. Okay, if it is helpful to you to kind of show the arrows, you can. If you don't like showing them that way, sometimes my students prefer to do it this way. Let me show you. We now know that calcium is combining with OH, and we now know that sodium is combining with Cl. Whatever is easiest for you to get this correct. So sodium is +1, Cl is -1, so we get NaCl. Calcium, on the other hand, is +2. OH from our polyatomic handout is -1. So we'll cross our charges to find that this is CaOH2. So you're switching partners. Okay. You're going to get a chance to try the second example here. NH4 has a +1 charge. SO4 has a -2 charge. Okay. At this time, please pause the video and attempt this practice problem. Please check your answer. These are the two products that you should have ended up with. NH4 is +1, F is -1, so they cross. Barium is +2, sulfate is -2, so they cross. Okay. Again, this is going to take practice. It is a skill that you learn with practice. Let's continue. Double replacement also has some subgroups, okay, and they are precipitation and neutralization. You'll want to be able to identify both of these as well. So a precipitation reaction is characterized by a solid being created, because a solid is known as a precipitate. For example, if we have NaCl, aqueous, plus silver nitrate, aqueous, double replacement, turns into sodium nitrate, which is aqueous, plus silver chloride, which is a solid. You would know that from the solubility rules, which we'll talk more about at a later time. Okay. There is something called a net ionic equation that also exists. In the net ionic equation, you basically take whatever the solid was and break it into its ions. So the silver chloride was the solid. And then working backwards, okay, but not actually showing the arrow backwards, you would get what its reactants were. So silver chloride is silver plus Cl minus. The other ions, the sodium and the nitrate that are not in the net ionic equation, are called spectators. A neutralization reaction is an additional subcategory for double replacement, and it is characterized by an acid plus a base forming a salt, any ionic compound, plus water. For example, HCl plus NaOH, an acid plus a base, producing NaCl, a salt, plus water. The last reaction type is known as combustion. And there's actually quite a few different types of combustion, but for us, we're going to say that combustion is a hydrocarbon, something made of carbon and hydrogen, plus oxygen, reacting to make carbon dioxide plus water. What's kind of nice with this type of reaction is that the prediction of products is always the same. You're always going to be producing carbon dioxide and water, and then you would go ahead and balance as well. So the products here for these examples are CO2 plus water, CO2 plus water, and then of course you would balance as necessary. Now that we've discussed all the different reaction types, you need to be able to practice predicting products a little bit more. So you're going to want to identify the reaction type in each of these reactions and predict the products. Look to see what's happening. When it's only two elements, they have to combine. When it's only one thing, it has to separate. Okay? If it's a hydrocarbon plus oxygen, it's going to produce carbon dioxide and water. So do not balance these, but at this time, please pause the video to identify the reaction type and predict the products for each. Okay. Please check your answers. The first one had to be a synthesis reaction, so I crossed my charges. Na plus 1, O minus 2. The second one had to be decomp, so I broke it apart, and then because they're diatomic, they needed a 2. The third one is single replacement, so the zinc replaced the hydrogen. The fourth one, again, is decomp, so I broke them apart. The fifth one, C6H12O6, is a hydrocarbon, so it's going to produce carbon dioxide and water. The sixth one is a single replacement. Again, this time the non-metal is replacing the non-metal. And finally, the last one is two ionic compounds, so they have to switch partners to form two more. So that's double replacement. As with everything else we have done this unit and this particular chapter, this takes practice. There's some practice problems for everything available on D2L. Let's continue on and talk about another type of reaction. Oxidation reduction, or redox as it's often referred to, is another reaction type. The test would have to tell you that there was a redox reaction because it's not super easy to recognize. Oxidation reduction always occurs in pairs, and it's based on the movement of electrons. One easy way to remember what takes place is OIL-RIG. It's an acronym. That stands for oxidation is loss of electrons, and reduction is gain of electrons. When something loses electrons, it becomes more positive. When something gains electrons, it becomes more negative. That's going to be important shortly. All elements have an oxidation number or state. Okay, for simple ions, usually it's the charge on the periodic table, so +1, +2, so on and so forth. So group 1A is +1, group 2A is +2, group 7A is -1, usually. Oxygen is usually -2, and then hydrogen can actually be +1 or -1, depending upon what it's bound to. Elements that are in their elemental state, so by themselves, not paired with anything, we say that their oxidation number is 0, no matter what. So if it just was sodium, or if it was just O2, or if it was just H2, or just lead, not paired with anything, we have an oxidation number of 0. So let's talk about the types of problems that you would have to be able to answer for oxidation reduction. The first type of problem would be one similar to this, where it says determine the oxidation number of each element below. Okay, the first one's pretty simple. Okay, we know that H is +1 and O is -2. Okay, let's do the next one together. Every compound has to have, unless it's given a charge, has to be neutral. So the overall charge has to add to 0. We know that H is +1. We know that oxygen is -2. But I have 3 of them. So overall, it's -6. N is the one that I'm looking for. Overall, the charge has to be 0. So hopefully you're finding, okay, -6 and 1 makes -5, so N has to be 5. If that doesn't work very well in your head quickly, you can also do this. 1 plus N, because we don't know what it is, minus the 6 for the oxygen equals 0, and you can solve algebraically, and you get that N equals +5. Okay. Please pause the video and try the next practice problem. K is a group 1 element, so it's +1. Oxygen we know is -2. There are 4 of them. So overall -8 plus 1 makes -7. So manganese has to be +7. The other type of problem could be something like this, where it says what's oxidized, what's reduced, and what are the spectators. To solve this one, you have to figure out charges of everything first. So NO3 has a -1 charge. We're going to keep that together. Iron, because of the 3 here, is +3. Zinc is by itself, so it's 0. NO3 on this side is -1 as well. Because of the 2's, both zinc and iron are +2. Notice we did nothing with coefficients. And then I'm just going to compare things. Nitrate doesn't change at all. So your nitrate is your spectator. Iron was +3, and it turned into +2, so it became more negative, so it's reduced. And our zinc went from a charge of nothing to a charge of +2, so it became more positive and is therefore oxidized. Okay. At this time, please pause the video and attempt the problem below. Lead and oxygen by themselves are 0. When they're in the compound, they're +2 and -2. Lead went from 0 to +2, so it's more positive or oxidized. And oxygen went from 0 to -2, so it's more negative or reduced. There is not a spectator in this reaction. We will continue our study of this chapter in the next video.